In the last class, we studied the directional derivatives. By definition, the direction derivative in a direction with some vector. That vector should be unit vector. Okay, so that's throughout the whole book. That's a condition. So be careful when you're given a vector which is not a unit vector, and just normalize it, and then the direction derivative is given by the gradient of the function, and the unit product was the unit vector. Okay. Today's topic is application of partial derivatives, and we try to find the maximum minimum value and the local maximum, local minimum value. This is then the second part of the lecture is about absolute maximum minimum values. So this is very similar to the section on optimizations in Math 165, I think. Yes, 165. Okay. So first of all, it's easy to understand the definition. A number is a local maximum value or local minimum value, right? And that means in a small neighborhood, the value of the function is always smaller or equal to that number. So let me give you one definition for local maximum value. Okay, a number, So here, here's a function. The function defined. This is in two-dimensional case. Okay, so be a function defined on a domain D. Okay, I'll open some domain. Okay, so we said that f of AB, this is the number, right? Is a local maximum value of the function f. Local means only a small number. Okay? If the value of the function is always small or equal to that number for x and y nearby the point AB. Okay? Nearby means that this is a D. There is a small neighborhood. You don't need to be the whole region. Okay, and for x. In this small neighborhood, as long as, in this small neighborhood, if the value of the function is always smaller than the value of the function at the point with coordinates A and B, then that is going to be the local maximum value. Now let me show you the picture. So here's a picture. Right? This is a z equals f of x and y. So if you look at the graph, it's harder to draw, this is z-axis, this is y-axis, this is the x-axis, okay? So you have a graph, something like that, okay? Then let me draw like this, okay? So this is a graph of the function, z equals f of x, okay? So at that point, this is local maximum. The function, this is local maximum point. And as a value, is going to be local maximum value, okay? So this is here's a point A1, B1, and this is another point A2, B2 above, right? So clearly, clearly Z1 equals f of A1, B1 is a local maximum value. Okay, it's a local maximum value, and this is not the highest point. The point is called local maximum point. Point means it's a point, it's not a number. Okay, with the 3 coordinates. So this point is not the highest point. You see, another point is higher than that. But locally, for x close to for x close to that point, for x, y, okay? When x, y close to A1, B1, and then the value of the function is always smaller than or equal to the value of the function at A1, B1, okay? So this is local maximum, it's clear from the picture. Now, the question is how do we how do we find the local maximum value? Okay, well, there is a necessary condition. If you look at the highest point, right, the tangent plane to that particular point must be horizontal. Got it? Yeah. So this is tangent plane must be horizontal. It's the highest point. Okay. So this tangent point must be horizontal. Right? Tangent plane are horizontal. Tangent plane is horizontal. Okay. So yeah, this means tangent point is horizontal. Now, how do we see that? Why is the tangent point is horizontal? We can show that. Yeah, this is the theorem. That's necessary condition. Okay, this is a theorem says that if the function has maximal or minimal at some point, and the derivative exists, then the partial derivative must be 0. Actually, the directional derivative must be 0 for any direction. Then you conclude that. Okay, you conclude that a partial derivative must be 0. So here's the definition. Okay? Here's the theorem. If the function f, okay, has a local maximum or a local minimum at some number in B. Now, if the function is differentiable, it's not differentiable, then you cannot say anything, right? And it is differentiable, and the first order derivative exists. Okay, so we just say it's and differentiable at that point. Okay, then the partial derivative must be equal to 0. And this is just a candidate for the point at which the function has local maximum, local minimum, but does not guarantee always. Okay, so we will have an example, just like if you recall the results in Math 165 on this topic in one variable. Okay, for the functions on one variable, then this number is called, actually this point should be called a critical point. Okay. Okay. So this is a necessary condition, and we can see that. Okay. Let's check. Let's look at some examples. Now, this is the equivalent to saying that. Okay. Equivalent to saying that the tangent plane at the point A and B and f of A and B, okay, is horizontal. Okay. Why? Because the equation for the tangent plane, is given by the following. Okay, we call that the tangent plane at any point, okay, at any point x0, y0, z0, where z0 is going to be given by this point, okay, is given by the following equation. Okay? The equation says that z minus z0 equals f okay? So that's the equation. So this is a plane, right? Horizontal means z equals z0. So that means these two coefficients must be 0. Okay? So the plane, the tangent plane is horizontal. How do you describe a horizontal plane, right? If and only if z equals z0, as you not, yeah. So it's just horizontal, right? So z coordinates all the same. So that means if and only if those partial derivatives should be 0. That's the reason you get those partial. But you know, so so the function, if it has a local maximum value or local minimum value at a certain number, then the partial derivative must be 0. Okay. So let's take a look at the following example. This is a function. It's going to be x squared plus y. It's x. Just the simplest example. Let's look at. Okay. So we want to find the local extrema, so local maximum and local minimum, if any. All right, so if the function has a local minimum at some number, right? Then according to the above theorem, this must be the partial derivative must be equal to 0. Okay. So we find out those partial derivatives first. Okay. So we know that if the function has a local, let's call the extrema, okay, at some number a and b, according to the above theorem, f of x and b should be 0. F of y sub y and b should be 0, right? So then you will see that 2a 0, 2b 0. So that means that point must be the origin. Okay. But that's all. This is obvious from the given function, because this is just a candidate. Okay, the point for the function for the points at which the function has a local extrema, local maximum, or local minimum. Okay. Now look at the function again. Look at the function. Look at the value of some function. You probably can get the answer directly. This function is always greater than equal to. Right? It's always greater than equal to 0. Right? It never be 0. So 0 should be the smallest value, which is going to be f0 and 0. That's obvious. Okay. So you don't need to go through the theorem, you don't need to use the theorem to find the local minimum value or local maximum value, because if you look at this function, it's easy for you to see that. Okay, so for any x and y, the value of function is greater than or equal to 0. And 0 is the value also of the function at its origin. Okay, so this implies we see that f has f has a local minimum at the point 0, 0. Okay. But what I did above before that just tells you if the function has a local minimum or local maximum at some point, that point must be origin. Now, actually, this is true. You can see that from the function directly. Well, the problem is how do we tell this function has local minimum or local maximum value if we already find the candidate, right? How do you check that? Okay. Now in Math 165, we have two theorems we can check. Okay. So we needed to do the following. So look at the function ft, right? I know f prime t is not equal to 0. So this is a critical number. But I want to know whether this, well, sometimes the formula for the function is very complicated, right? It's harder to do. So if you can show, okay, so that's the first theorem we know that is if, okay, if the function, the derivative is going to be negative for t less than t naught, and the positive for t greater than t naught, then you will see that the graph must look like that, negative, so it must going down, then going up, okay? So this, yeah, this is a negative, and this side is greater, positive, so it's increasing. So that means f has a local minimum value at this point, right? So this is a one-dimensional case. The second theorem says that if the second derivative, okay, is greater than 0, okay, that's it. You don't need to look at the sign of the derivative. That's called second derivative test. So then this means I don't mention some small conditions. Then the means is this one. This one has a local minimum value at t naught. Okay. Why this is true? Because this second theorem implies the first one. Right? The second theorem implies the first one. Well, the reason is, if this is a positive, means the second derivative is positive for t close to t naught, right? Then you know that f t naught is going to be 0. So that means the graph for the y equals f prime t is increasing. Increasing means on the left hand side of t naught, f prime t should be negative, right? For t less than t naught, and on the right hand side, the derivative should be positive. That's why second theorem implies the first one. Now, how can I use this theorem to get some result to check? Now we have two variables, right? Whether this function has a local maximum value or local minimum value. Okay, here's the point. Okay, so we consider a function f of x. Okay, okay. We know that f prime a b equals f. The partial derivative, they're all 0. So this is just my candidate, right? I want to know whether this function has a local maximum or local minimum. But if it's hard to check whether the function is greater than or equal to the value function at this point, how can I see that, right? I cannot tell the derivative partially, right? So what I'm going to do is I consider the direction derivative, okay? So this is a picture. Okay, I assume this is a local maximum point. Okay. So what I'm going to do is I look at the direction derivative. That's why direction derivative is studied, first. So what I'm going to do is I consider an arbitrary direction, u and v. Right? So then you get the corresponding function. That function may be called h of t. Okay, this is going to be f a plus tu b plus tv, right? So if the function has a local maximum point, then then h of t should have a local maximum value at t equals 0. Okay, so think about that. So f, okay, so let's erase that. So if h of t less than or equal to h of 0, right? For any direction, then you can see that f of x and y less than or equal to f of a and b for any x and y close to AB. Okay, so that's the idea. Okay, if you restrict to any strict line nearby passing through that point, the value of the function in one variable right now in t, if it has local maximum value at t equals 0, that means the function has a local maximum value at that point. So how do I check this? I can use a second derivative, right? I use a second derivative, okay? So how can I guarantee this is true? So this is a true if the second derivative, okay, at t0 is going to be second derivative test using them in the in mass 165. So this should be greater than 0. Okay, if this is 0, then it implies for t close to t equals 0. Okay. Of course, we assume that it's we already know we already know that because this condition, right? We already know that t, this is always 0, okay? This is the derivative is already 0. Okay, this is because the partial derivative is 0. So h prime 0 is going to be 0. The reason is this is a directional derivative in u and v f at point AB. So partial derivative 0, this must be 0. All right, so how can I let's calculate? Okay, I'm going to calculate this. Let's look at the first derivative. The first derivative is going to be fx a plus tu b plus tv, and here's u. Okay, and plus it's a v. And when t equals 0, it's a 0 because the partial derivative is 0. The second derivative, when you differentiate twice, and you get xx a plus tu b plus tv, then you get u squared. Okay. Then you get fxy a plus tu b plus tv and uv. Okay. Then you differentiate the second term. V and U, and then plus FYY. Yeah, it's getting more and more complicated. Right, so you get those terms. All right, so let me evaluate at the 0. When I evaluate the 0, I get fxx and b u square, fx and y, and b uv plus fyx b vu, and plus fyy and b v squared. So this is a quadratic form in linear algebra in Math 171. I assume you took that course. This can be written in the form a matrix right? But f sub yx, f sub xy is the same. And this is going to be like written in that form. This is in the matrix product form, Okay, if you took a mass 171, you're familiar with this. So we want to make sure this is a what? This is a negative, right? Remember, if this is a negative, means the h of t has a local maximum value. Let's go back, okay? Let's go back to this problem. Okay. So I'm given this function. I already have a candidate critical point, so partial derivative of 0. Then I restrict the function to one line passing through that point. So I get h of t. I know h of t prime is going to be 0. Okay, the reason is the partial derivative of 0. Then I want to make sure when the function has a local maximum value. The function f has a local maximum value if and only if h of t has a local maximum value. That's just one variable, and for any direction, right? In any direction. So that's those two equal, right? So how can I check whether the function h of t has a local maximum value? I just needed to use a second derivative test from mass 165. The second derivative test is going to be greater than 0. The second derivative is going to be 0. That's guarantee the function has a local maximum value at that point. Okay. And then I calculate the second derivative of the function t for any given direction uv. I find out this matrix. Okay. So I conclude the second derivative test for function with two variables. The second derivative test says that suppose the second partial derivatives are continuous on the disk with a center in B. Okay, this means the second derivatives exists. Okay, suppose the second partial derivatives of f, right, are continuous. I just say nearby the point A and B, okay? And I assume that this is going to be 0. Okay? Right. Then you want to know whether this matrix, yeah. So I'm going to state the theorem in a slightly different way. I look at this from linear algebra, right? From mass 171. You see? So the first one, if that matrix, okay, I'm not, yeah, let me put the details, okay? If that matrix in the B is always negative, okay, for any u and v not equal to 0, okay, then f has a local maximum value. Okay, so it's very similar. It's like a second derivative. A maximum value at that particular point. Okay. And similarly, if this matrix, okay, I'm not going to copy that, is greater than 0, okay, for any u and v for any direction which not equal to 0, then the function has a local minimum value. At that point. Okay. The only problem is how do you check that? Whether it's always positive. So in the book, that gives you see, look at the matrix A. You have a matrix, symmetric matrix, right? And let's just use I'm going to use any letters. Let's say A11, A12, A. Now this should be symmetric. So yeah, it's okay. A12, A21, A22. Okay, given symmetric matrix, right? We can see that we can show when this is going to be we call it positive definite or negative definite. Okay, so negative definite. How can I check whether it's going to be negative definite? Okay, right? How do I check this one is true? Okay, so from linear algebra, this is a negative for any u v not equal to 0 if and only if the eigenvalues of this matrix is going to be negative. Okay, so the eigenvalues lambda 1, lambda 2 are both negative. Okay, but how can I see that from the matrix? Then if and only if A11 is negative and the determinant of the matrix is going to be positive. Okay. This is a review of the Math 171. Now, how about this is a negative definite, okay? The matrix is called negative definite, okay? This is called negative definite. If and only if you can find the eigenvalues given matrix 2 by 2, right? Now, positive definite, okay? So give the positive definite means U and the V, A11, A12, A21, A22. It's for any UV not equal to 0, then you just need to make sure all the eigenvalues is positive. All the values are positive. But if you look at the matrix, how can I check whether the eigenvalues are positive? You just need to look at the first number, A11 is positive, but and then the determinant should be also positive. So determinant is always positive, okay? Doesn't matter in which case, only these numbers. Okay. And another importance is if it's not definite, if two eigenvalues, one has an opposite sign. If two eigenvalues and opposite sign, then the function, the graph of the function locally looks like a saddle surface. Okay, so then the function does not have a local maximum value, local minimum value. So I'm going to go back to this the theorem. See here, this is a theorem, right? Second derivative test, and you will see that what happens if it's not always positive definite, it's not always negative definite, negative or positive definite, then the function does not have a local maximum, local minimum value. Okay, so I have to go back to the third part of the theorem. So the third part of the theorem is if this matrix has opposite sign eigenvalues. Okay, opposite sign eigenvalues. I should say changes signs. Okay. Okay. If it changes, if it changes signs, then the function does not have a local maximum. Right, the function is not, the value of the function is not a local maximum or minimum. Right? But how do you check whether or not this changes sign? Right? How do you see that? That means, i.e. the eigenvalues. Okay, here's a node. That means lambda 1, lambda 2 have the opposite sign. Okay. So how do I see this has opposite sign? I needed just, this is equivalent to saying that the determinant is going to be negative. And the reason is the determinant is going to be lambda 1 times lambda 2. Okay, it's going to be lambda 1 times lambda 2. Two numbers have an opposite sign if and only if the product is negative, right? That's it. If they both have a negative sign, if they're both positive signs, it's going to be product is going to be positive. So as long as the product is going to be negative, then the product is going to be negative, then they have the opposite sign. Okay, so so the function, why the function does not have a local maximum, local minimum value at that point? Because the function is going to be approximated by this by a quadratic. Yeah, it's hard to explain here. It's approximated by the function involves by a quadratic function, right? If that quadratic function does not have a local maximum value or local minimum value, then the original function will be the original function does not have a local maximum value, local minimum value. Okay. So using this theorem, we are going to easily check whether the function has a local maximum value or local minimum value. Okay. So I'm going to consider the following function: x to the fourth, y to the fourth, minus 4x times y. Okay. So clearly, the graph passing through the origin, because when x equals 0, y equals 0, z equals 0. Okay. We are going to find the local maximum and minimum value, okay, of this function. Now it's harder to tell. It's not quadratic function. I cannot draw the picture easily. Right? And then we want to find the local maximum and local minimum value. Right? So first thing is find the candidates at which the function has local maximum and local minimum value, right? So we find the critical point of this function. So find the partial derivative is a 4x cubed minus 4. 4x cubed, 4y. And the 4y cubed minus 4x. Right? So we set them to be 0. I want to see if any solutions I can get. I got, I got two equations. How can I solve that? Right. First of all, there are trivial solutions. X equals 0, y equals 0 is a solution, but then maybe they have other solutions. Use a substitution, that's right. So use substitution, let's find, what is x, right? X is going to be y cubed, and I put into the first equation y cubed and cube minus y equals 0. Well, okay. So this is going to be y to the 9th power minus y equals 0. and you take a y factor. Okay. So you got two solutions, y equals 0, y if equals 1. Now, how do I solve this? Well, this implies, where is this from? Okay. So this implies y to the fourth is going to be 1. This implies y squared equals, this implies y equals minus 1, plus minus 1. There are two solutions, there are no other solution, okay? So now you have a total 3 different values for y. But I know x equals y cubed, right? So that means when y is 0, x is 0. So you get first set of solution. And then you have when x equals 1, y equals 1. When x equals -1, y equals -1. Okay, so you get 3 points. And I have to check one by one. Okay, at those 3 points, the first partial derivatives are all 0, right? I needed to look at the matrix. Right? I needed to look at the matrix of the second derivatives. So I have to find out x. Yeah, where's the function? I forgot. Okay. So I need to get f sub x. So f sub x, then it's going to be 12x squared. Okay. F sub yx is going to be f sub y, xy, yx is same. So they are going to be, when a differential with respect to y, I get a -4. Okay. Then f sub yy, and I'm supposed to get, 12y squared. Okay. So you get a matrix, okay, but you have to evaluate at those points. Okay. So the first matrix at 0, 0. The matrix is going to be 0, -4, -4, and 0. Okay. Yeah, this is a matrix. Okay. So clearly, this matrix, the determinant is going to be negative. Okay. So the D, which is the determinant, is going to be -16, which is negative. So this means has opposite eigenvalues. Okay, that means it changes signs. Okay, so the function, so this is a set point because the function does not have a local maximum, local minimum at that point. Okay. So what I can say that f00 is not a local maximum or minimum value. Okay. I probably will draw the picture for you later on. Local is because a function later we're going to study the Taylor expansion. So the function determined by is approximated by those partial second order partial derivatives. Okay. At 1 and 1. At the 1 and 1, I get 12, 12, -4, -4. So the matrix is going to be 12, -4, -4, and 12. Okay. at that particular point, and you will see that 12 is positive, and the determinant is also positive, right? Look at that, 12 is greater than 0, A11, right? And the determinant of this matrix is going to be 12 squared minus negative 4 squared is positive, right? Does not change the sign. So this implies F1 and 1 is a local, it's going to be local minimum value. Why minimum? Because all the eigenvalues here are positive. This year, yeah, eigenvalues must be positive. You can find eigenvalues of this matrix, okay, if you want. Eigenvalues are positive. The graph looks like it can curve up. Yeah, the graph looks like that. Okay, the graph looks like that. And so this has a local minimum value. Okay. And the same story here. By at that particular point, I think it's the same. You get same matrix because x squared y squared. So you will get this, right? And clearly this one, again, the same story. A11 is going to be 12 greater than 0. The determinant is also going to be positive. So the function, the value of the function at that particular point is a local minimum. It's harder to draw the picture, but you have if you look at the graph, you have two low mountains like that nearby, okay, and there's a center at the origin, and it looks like a saddle point, okay, it's the origin. Okay. So it's hard to draw the graph, but I can. This is local, yeah, this is local minimum point, yeah. So if we have to draw the graph, probably if you have to draw the graph, where's the point? Here's a one, here's another one. Okay. So the graph maybe looks like, yeah, it's hard to draw it. So maybe it looks like that. This is the direction. Here's the doing. Yeah, has a local minimum value. Yeah, it's going. But anyway, there was two local minimum value. Then it's going down. You can put some water there. Okay, it's like a loop. Okay, and but it's not. Oh yeah, some place can curve up, some can curve down. So it's harder to draw the picture. But imagine there's two local minimum points there. Okay. Now, why the sign of this matrix gives you the give you some information about local behavior of the function, because at the point A and B where the partial derivative is going to be 0, the function, okay, can be approximated by this matrix. Here's x minus a, y minus b, and this is a matrix, okay? And this is going to be x minus a, y minus b, and this is a partial derivative. Okay? Then you have a high order terms, but those high order terms, yeah, there's some high order terms that's called the aperture. Okay, that's high order terms. So this is almost equal to 0, very close to 0 when x and y close. So this part completely determines the graph, local behavior of the graph, local behavior of the graph, right? and this is a yeah, the epsilon actually, the limit as x or y approaches a and b, this epsilon divided by x minus a square, y minus b square is going to be 0, okay? Yeah. That's right. So this term is compared to the matrix here is a very small number. That's why you can. So you want to look at the local behavior of the function, just needed to look at the sign of this matrix. Okay, if it's positive definite or negative definite, or change the sign. If it changes sign, the graph looks like, it's like it's called, we call it saddle surface. Yeah, just, and if it's always positive, then the graph has a local minimum point. Right? If it's always negative, then the graph has a local maximum point. Okay. All right. So we can also look. Yeah, let's look at another. Let's look at another point. Another example. Yes. Here's another example. Take it from the book. Yeah, I'm going to do 11. Do number 10. Okay. F of x is going to be 2 minus x to the 4th plus 2x squared minus y squared. All right. So this is not a quadratic. This is not a quadratic function. It's not a linear function. It's not a quadratic function. So it's the graph. It's hard to draw the graph. Okay. But if you use a graphing calculator or some other software called MATLAB or Mathematica or Maple, you can draw the 3D graph and can see where the graph, how many local maximum point, how many minimum point, you can see that. But the graph is only local graph. That's all we have to start the thing. We say, oh, the computer can give me everything. But the computer screen is limited, right? And so you do need a mathematics to understand the graphs, because you cannot guarantee out of the screen whether you don't see the whole picture, right? It's hard to tell whether the function has no maximum points or minimum point, right? Outside a very large region. Okay, so take a look at this. I want to find local maximum value and the local minimum value. Okay. So how do you do that? Well, still find the point in the xy plane at which the function has a local maximum value, right, or minimum value. So I needed to look at the partial derivatives. It's going to be negative 4x cubed minus plus 4x equals 0. Okay, and the second one is going to be the partial derivative, it's negative 2y equals 0. Okay. Yes. All right. So y is always equal to 0, right? The first equation, if you get rid of 4, you get this. But you can take x out. Then you get this, right? So you get x equals 0, x squared equals 1. So x squared is plus minus. So you have 3 solutions. but the y value is always 0. So they are on the x-axis. There are 3 points, special points, at which the function might have local maximum point, local maximum value, local minimum value. Okay, so in order to check whether the function has a local maximum value or local minimum value at those 3 points, okay, I needed to calculate the matrix. Right, so the matrix is going to be the second derivative, right? The second derivative. It's going to be negative 12x squared plus 4. Then partial derivative with respect to y, that's going to be 0. Great. So this matrix is already diagonal. This is also 0 and fyy. It's going to be negative 2. So this is a very special matrix. This is the matrix is already is a diagonal matrix. Okay, only the numbers on the diagonal will be not equal to 0. Okay, so the matrix, you will see that. So I put them together. Okay, how do I express them easily? So let A to be fxx, right? fxy, fyx, fyy. Okay. So to save time, so when I evaluate x equals 0, y equals 0, the matrix is going to be 4, 0, 0, negative 2. Okay. Oops. All right. What happened? Where's my file? Oh, okay. Nope. Couldn't find my file. Okay, it's here. Close. All right, so we're back. So this is a matrix. When you look at this matrix, does this matrix changes the corresponding quadratic form? Does it change the sign? I think it's clearly changes the sign. Okay, so the determinant of this matrix is going to be negative 8, so which is negative. So what does that mean? That means this is the function does not have a maximum value or minimum value at this point. So f00 is not a local maximum or minimum. Okay? And in this case, this point is called a set point. Okay? The graph looks like the graph will cross the tangent line. Graph looks like that. Okay, in one direction, yeah, it's hard to draw it. It's like that, you know. But on the other side, so you can sit on that. Okay, so it's called saddle part. Okay. Yes. So there's one, this is not going to be a local minimum point or local maximum point, because in one direction, in this direction, the value function going down, right? It decreases, but in other direction, the value of the function increases. So this is not a local maximum value. Yeah, f of 0, 0 is not going to be local maximum value, not local minimum value. Okay, it depends on the direction you choose. So now at x equals 1, y equals 0. At x, we have 3 points, right? X equals 1, y equals 0. Then what do we get? When x equals 1, I think it doesn't matter which, because there's x squared there. So x plus minus 1 is okay. X plus minus 1. So I get the matrix. Negative 12 plus 4 is going to be negative 8, 0, 0. And then the other one is negative 2, right? Yeah. Negative 12 plus 4, negative 8, and then negative 2. Okay, if you look at this matrix, clearly it's negative definite, right? So it's negative definite. It's negative definite. The determinant of A is positive, but negative 8 is negative, the first one. Okay, so that equivalent to saying lambda 1 is negative, lambda 2 is negative. But actually, those two eigenvalues clearly, one is negative 8, the other one is negative 2, because it's already, it's called a diagonal matrix. It's in the simplest form. Okay, so that both are already negative. If you find the eigenvalue and it's about negative, okay? So that means, think about the second order derivative is negative. There's a graph must concave down in that, nearby that point. So this implies f plus minus 1, 1, 0, okay, is a local maximum value. Okay, is a local maximum value. So you can calculate the value even. Okay, so when y equals 0, x plus minus 1, I forgot my original function. Okay, original function is here. It's 2 minus, yeah, 2 minus from the book. Yeah, so let's look at the value of this function. It's going to be 2 minus negative 1 plus or minus 1 to the 4th power plus, is that number? 2x squared y squared, yeah. So 2 minus 1 plus 2, that's going to be 3, okay? So 3 is the local maximum value of the function. 3 is the local maximum value of the function. Now, in a few words, I have to talk about absolute maximum value and absolute minimum value. It is similar to the function in one variable. I'm going to state the theorem: if the function is continuous, then it must have a maximum value in the neighborhood, in this domain. Okay, it's close bound. Yeah. So here's a theorem. It says that. Okay. So if we assume that the function, if f is a continuous function, defined on a closed bounded domain. Now, bounded set V, okay, in R2 or even high dimension, okay. Then then the guarantee the function has a local, has absolute maximum value and absolute minimum value somewhere. Okay. Then the function attains an absolute maximum value somewhere, okay, and an absolute minimum value. Okay, somewhere from at some point. Okay, so this is some point in the set D. Okay, so so that means we don't have time to do exercise today. So that means if the function, this is a bounded domain D. Okay, closed set. Closed means it's not open, including the boundary. Okay, including the boundary. So if the function is not broken, think about it, right? So this is a graph. Definitely can find the highest point and lowest point. Okay, at the highest point, the function attains an absolute maximum value. At the lowest point, the function attains the absolute minimum value. Now, how do you find the absolute maximum value? How do you find the absolute maximum value? If the point is inside the domain, then that point must be critical point, and the partial derivatives, you have to look at the partial derivatives, right? If the point on the boundary, then you have to look at the value function along the boundary. So it's more complicated than the function in one variable. In the function in one variable, how do you find the absolute maximum value? You find the critical numbers, right? And the critical number inside the interval. Then you look at the value of the function at the critical values, and at the endpoints, that's only 2 endpoints. Then you compare them. You choose the one, largest one, that's the absolute maximum value. But now our function is defined as a domain. So the endpoint, so-called endpoint, will be the boundary. Okay, so it will be like a circle, like a square. So you have to look at all the possible values, but usually it's that simple. It's easy to see that. Okay, and unfortunately, I don't have much time to discuss, but this is the idea for the, this is the idea to how to find absolute maximum value. Okay, so we're going to get a quiz on Monday, on Friday. So this section will be a test, but I'm not going to ask you to find absolute maximum value, but do your best, okay? We're going to continue to discuss how to find absolute maximum values. Yeah. On Mondays.